proof of the power rule for integers. The power rule is the rule that tells you how to differentiate x to a power. In this case, the proof is for integer powers, not for fractional powers or decimal powers. So the rule says that the derivative of x to the n is n times x to the n minus 1. That's one of the basic differentiation facts, and one that, though not a rigorous proof, you can give a pretty good justification for that, and you'll have an opportunity to do that. And the main question is, how in the world would you go about starting to do this? And since this is coming very quickly after just defining the definition, there's no way to really do this other than to go to the definition. So here's the definition of the derivative. And in this case, f of x is x to the n. Therefore, applying the definition of the derivative, we're looking at this as being the expression that we have to take the limit of. And to do that requires a little bit of memory work to think about what this binomial raised to an integer power looks like, and that comes from finite mathematics. You may or may not have seen that before. Hopefully you've seen that before. But essentially, when you expand a binomial to an integer power, you get a pattern of coefficients that are related to the Pascal's triangle. And when you expand that, the first term will be x to the n. The next term in the nth power expansion of this binomial will be n x to the n minus 1 times h, and then a bunch of other terms. And these other terms, the only thing that's really important about them is every one of them except this first term has an h in it. So when you expand this with the binomial theorem, you get an x to the n, and you get a minus x to the n, and the x to the n's cancel. And then you have terms here that have h to the first, h to the second, all the way up to h to the n in them, and you can factor out an h. So once you've gotten x to the n minus x to the n, which is a 0, then you got an expression that looks something like this with a whole bunch of terms in there, and every term has an h in it. So once you factor out one h, what you're left with is an expression where the h's cancel, and every term that is left in the numerator after the two h's cancel has an h in it except for the first one. So the first one has no h in it. The next term has an h to the first up to h to the n minus 1th, whatever n is. And when you substitute in h equals 0, now you can just do the substitution since the h is canceled, and all of these other terms go to 0, and what you're left with is simply the power rule. Now, this only works for integers, and there's a proof in the back of the book which works for non-integer values, but it is true in general. Just to refresh your mind about the binomial theorem, here's a little Mathematica notebook. I didn't really know how to do this, but I typed in binomial in the help window in Mathematica and got this example. I just cut it and pasted it in here, and this essentially duplicates Pascal's triangle. Right, 1, 1, 1, 1, 2, 1, 1 and 2 is 3, 2 and 1 is 3, and 1, if this is not familiar to you, ask one of your instructors. 1 and 3 is 4, 3 and 3 is 6, 3 and 1 is 4, and these turn out to be the coefficients when you expand a binomial. If you take x plus 1 squared, you would get 1x squared plus 2x plus 1. If you take x plus 1 cubed, you will get x cubed plus 3x squared plus 3x plus 1. If you raised x plus 1 to the 5th power, these would be the coefficients. And the thing to notice is when it's the 5th power, the second coefficient is 5. When it's the 4th power, the second coefficient is 4, and that's the thing that shows up in the power rule. So messing about with that just a little bit, this is simply one that has the letters in there. This is to expand a table. Essentially, you can just copy this and mess around with it, and you can expand the x plus h to the n for n is 0 to 5. You do have to say expand, or else it doesn't expand these out. But here again, this is what you would expect to see if you expanded x plus h to the 5th. It would be x to the 5th, and then 5x to the 4th h, and 10x to the 3rd h squared. And notice that the exponents on the variables always add to 5 if you're raising it to the 5th power. And if that's a bit interest to you at all, you can look up, you can mess around with the mathematical worksheet, which will be posted, and you can also look up Pascal's triangle, binomial theorem. You can take a finite math course.